How can something with no mass at all carry energy across the vastness of the universe, brushing against your skin as sunlight, warming the air, painting the world with color, and yet never gaining even a moment of rest? If this quiet journey brings you a sense of wonder, and if you enjoy drifting through the secrets woven into the fabric of the cosmos, a gentle like or a soft tap on subscribe truly supports this little corner of the universe where curiosity moves at its own peaceful pace. So now, as you settle in and let the day loosen its grip, let your mind rest gently on this single question, following it like a faint glimmer of light traveling outward through stillness. A photon begins as a tremor in an electromagnetic field, a pulse of oscillation created whenever a charged particle changes its state. An electron shifting orbit around a nucleus, a quark adjusting its alignment deep inside a proton, a thermal vibration rising inside the surface of a star. Many origins, but all of them share a single truth. Every change in a charged particle creates a ripple in the field, and that ripple can detach, free itself, and travel outward as a self-sustaining wave. This is the photon, the quiet courier of the universe, the bridge between electromagnetism and the experience of sight and warmth. And yet, despite the power it carries, the photon has no mass. It does not weigh anything, does not sink into the gravitational fabric by its own inertia. It merely follows the shape of space-time itself. To imagine how it holds energy despite its weightlessness, picture an ocean wave. Water moves locally, yet the wave itself carries energy across the surface without transporting the ocean with it. The water molecules rise and fall in place, but the wave's energy moves forward at a speed determined by the depth and shape of the sea. A photon behaves with a similar grace, though it is far more fundamental. There is no substance underneath it, no medium of water or air guiding its path. Instead, the photon is the wave itself, a pure oscillation in the electromagnetic field, moving through space-time at a fixed and uncompromising velocity. The cosmic speed limit, the speed of light. Einstein's equations tell us that energy and momentum are entwined even for particles with zero mass. A photon cannot be at rest because the mathematics of special relativity reveals that a massless particle resting still would require infinite energy, an impossibility. So nature chooses the only stable configuration: movement, pure and absolute. A photon must always travel at light speed, and because it does, it possesses momentum. That momentum is tightly bound to its frequency, the rate at which its electromagnetic wave oscillates. High-frequency photons, like gamma rays, tremble with frantic energy. Lower-frequency photons, like radio waves, stretch their oscillations across long, lazy wavelengths. Yet all follow the same fundamental principle. The higher the frequency, the greater the energy carried by the photon, even though its mass remains forever zero. As you lie here, you are bathed in an entire spectrum of these weightless messengers. The warm glow from a lamp, the soft shimmer of reflected moonlight, the calm dimness of your room. All of these are fields trembling, sharing tiny quanta of energy with your eyes and skin. Inside each second, countless photons touch you, but none of them have mass. Their energy comes from their vibration alone, not from any intrinsic substance within them. They are not small beads of matter. They are movement itself, organized into packets by the rules of quantum mechanics. When Maxwell uncovered the nature of electromagnetic waves, he revealed a truth so elegant it still hums through physics. Oscillating electric fields create magnetic fields, and oscillating magnetic fields create electric fields. They sustain one another like two hands passing motion back and forth. This interplay forms a self-propagating wave, one that requires no medium, no physical thread to travel along. When quantum theory later revealed that this wave can exist in discrete packets of energy, the photon emerged. Not as something with a shape or form in the classical sense, but as a quantized excitation of the field. Its energy is simply the rhythm of its oscillation. Higher rhythm, more energy. Lower rhythm, less. Imagine a guitar string plucked gently. The string vibrates, and the air around it vibrates in sympathy, carrying sound outward. But imagine instead a cosmic string, hidden beneath the physical world, not of matter but of pure field. When it is plucked, its vibration does not disturb air but space itself. The photon is the smallest unit of that vibration. The guitar string analogy simplifies a reality much more subtle, but the essence remains. Energy can be stored in oscillation rather than in mass. You might think of a photon as a piece of information about a change that happened somewhere. A whisper that an electron shifted levels. A signal that a charged particle moved. And because the universe is bound by conservation, energy released in one place must go somewhere else. The photon carries that energy, embedding it not in mass but in frequency. This is why light from the early universe stretches as space expands, its wavelengths lengthening, its frequency lowering, its energy gently decreasing as it travels across billions of years of cosmic evolution. The photon gives itself to the universe simply by existing within it. The Planck-Einstein relation tells us that the energy of a photon is tied directly to its frequency, E h x f. Here, h is Planck's constant, a number woven so deeply into quantum behavior that it sets the scale at which uncertainty and discreteness appear. As the frequency rises, energy rises. As frequency falls, so does the energy. But nowhere in the equation does mass appear. The photon has no need for it. The universe has given it a different way to exist, a different way to participate in the exchange of energy. And yet, even though it has no mass, a photon can push on matter. Solar sails catch light like a gentle wind, and photons transfer momentum to them, inching spacecraft forward without fuel. The pressure of sunlight shapes the tails of comets. Photons streaming from massive stars can blow away gas and dust, sculpting entire nebulae. In laboratories, lasers trap atoms and cool them to temperatures inches above absolute zero by pushing on them with streams of massless particles. This is possible because momentum is tied not to mass alone, but to motion and energy. In the case of a photon, momentum arises purely from its frequency. It is like a dancer with no weight whose movement alone can shift the entire stage. To understand this more deeply, imagine a river with no water. Only movement, only flow. A photon is that flow. It is kinetic elegance without substance. When it meets an atom, the atom feels the nudge not because the photon has mass, but because the change in electromagnetic field influences the charged particles within the atom, transferring energy through force rather than collision. The photon doesn't hit the atom the way a ball hits a wall. Instead, their fields intertwine for the briefest instant, exchanging energy in the language of probabilities and quantized transitions. This is why the photon is central to quantum field theory. It is the mediator of the electromagnetic force, the carrier of all interactions between charged particles. Every time two charged particles influence one another, even across a distance, They do so through the exchange of photons, sometimes real, traveling photons, sometimes virtual ones that exist only for the brief flickers allowed by quantum uncertainty. But all of them operate on the same principle: field fluctuations carrying energy and momentum without the need for mass. When you picture light traveling across the room, you might imagine tiny physical entities darting through space. But this is a human intuition shaped by a world of objects and substance. The photon is more abstract and more delicate. It is a condition of the electromagnetic field, a quanta of its vibration. It is not a marble, not a grain, not a point. It is a ripple with no medium, a piece of motion, a unit of energy bound to a rhythm. As you let your thoughts quiet, consider what this means for the simple act of seeing. When you open your eyes in daylight, the colors flooding into your vision are carried by photons born in the sun's fusion core, created when hydrogen nuclei merged into helium, releasing energy that took thousands of years to reach the surface and only 8 minutes to journey through space to you. Those photons, massless and tireless, have traveled across vacuum, through gravitational curves, through the expanding fabric of space, carrying with them the energy of ancient nuclear reactions. And the entire time, they weighed nothing at all. Yet they illuminate your world. They warm your skin. They define your perception of shape, color, and depth. Their energy enters the photoreceptors of your eyes, triggers molecular changes, sends signals to your brain, and allows you to form a coherent picture of reality. These signals are not carried by mass but by motion. You perceive because the universe vibrates, and those vibrations reach you. Light is the oldest storyteller. Long before words existed, long before life arose, light traveled through the cosmos carrying the memory of events, the birth of stars, the death of galaxies, the shimmer of cosmic background radiation from a time when the universe was only 380,000 years old. Photons have been moving since then, stretching as space expands, cooling with the universe, yet continuing their journey. They are the ancient breath of the cosmos, and though they weigh nothing, they bring with them the weight of time. As your breathing slows, imagine yourself drifting in the path of these ancient messengers. Each photon traveling at light speed experiences no passage of time, from the moment of its creation to the moment of its absorption. No internal clock ticks. It is born and arrives in the same instant from its perspective. A gamma-ray photon traveling across 10 billion light-years experiences that journey as zero time, a single continuous moment. For you, this is unimaginable. For the photon, it is simply the way existence works without mass. And yet, despite its weightlessness and timelessness, the photon brings energy across that unimaginable distance and delivers it exactly where it needs to go. This is the essence of how a photon carries energy without mass. It is a wave that needs no substance, a vibration that needs no rest, a traveler that ages not at all. It carries energy because nature has allowed energy to reside in frequency, not just in matter. It interacts with the world because fields are not passive. They are dynamic, responsive, sensitive to every tremor. And so, as you lie here, surrounded by the quiet, you are immersed in an ocean of these massless travelers. They touch you gently. They reveal the room around you. They whisper the history of stars. You feel none of their momentum, yet they shape everything you know. They are weightless, but they are never empty. They are the rhythm of the universe given form, the soft thread that binds perception to physics, the bridge between matter and motion. You might imagine how astonishing it must have been when James Clerk Maxwell realized that light itself was nothing more than a wave in the electromagnetic field. 4 equations, quiet and precise, written in the 19th century, revealed that oscillating electric and magnetic fields could sustain one another and travel outward at a particular speed. When Maxwell calculated that speed, he found a number eerily close to the measured speed of light. And in that moment, humanity learned that illumination, warmth, and color were not separate forces, but expressions of a single field permeating the entire universe. Light was no longer just a phenomenon you could see. It was a law of nature written into the fabric of reality itself. Later, when Albert Einstein introduced the photoelectric effect, he showed that light sometimes behaved not as a wave, but as localized packets of energy. This experiment, where ultraviolet light knocked electrons free from metal surfaces, defied every classical explanation. The energy of the emitted electrons depended only on the frequency of the incoming light, not its intensity. More brightness could not compensate for lower frequency. Only higher vibration could free the electrons. Einstein's interpretation, that light came in discrete quanta, earned him the Nobel Prize and gave the photon its name, paving the way for quantum mechanics to emerge from the confusion of early 20th century experiments. As you lie in the stillness of your room, imagine the significance of this discovery. A photon carries energy because its frequency dictates its power, and its frequency arises from the trembling of the electromagnetic field itself. There's nothing inside a photon, no gears, no atomic structure, no mass. Its entire existence is written in rhythm, like the pure tone of a perfectly tuned instrument, sustained across the cosmic void. Quantum mechanics deepened this understanding. Experiments like the double-slit experiment, first performed with light by Thomas Young, revealed that photons behave both as waves and as particles, depending on how they are observed. Send them one at a time through 2 slits, and each photon lands on a screen as a tiny point of light. But over time, a wave-like interference pattern forms, suggesting that each photon traveled through both slits simultaneously. This gentle paradox, still discussed in modern physics classrooms, reflects the profound nature of how energy without mass navigates reality. The photon does not choose one path. The field explores all possibilities, and only upon interaction does the world crystallize into a single outcome. Later experiments, such as those performed at Bell Labs, at the Cavendish Laboratory, or at SLAC, probed ever deeper into this duality, revealing that energy can be carried through probability waves just as effectively as through localized particles. When scientists at CERN examine high-energy collisions, they watch photons convert into particle-antiparticle pairs, transforming their energy into mass. Here, again, the photon's power is revealed. Even without mass, it carries enough energy, if its frequency is high enough, to create matter itself. In these collisions, gamma-ray photons can become electrons and positrons, their energy frozen into mass by the rules of relativity. This connection between mass and energy was one Einstein carefully expressed in his famous equation, E SARS mc2. Mass can become energy. Energy can become mass. A photon, though weightless, sits at the heart of this interchange, serving as a messenger between the two faces of physical reality. It is not that the photon needs mass to carry energy. It is that mass is one specific way energy can exist, and the photon is another. In many ways, the photon is the purest expression of energy, freed from the constraints of inertia, allowed to move at nature's maximum speed because nothing within it anchors it to a slower state. As you rest more deeply, let yourself imagine how remarkable it is that photons do not experience time. If you follow the mathematics of relativity, you see that for any object moving at light speed, time does not flow. Length contracts along the direction of motion. The journey across a room or across a galaxy becomes the same to the photon, a single, indivisible moment. When the cosmic microwave background radiation was emitted roughly 13.8 billion years ago, the photons released then have been traveling through expanding space ever since. Yet, from their perspective, their emission and their arrival in our detectors, such as those on the Planck satellite, occurred in the same instant. These massless waves have carried energy across the entire history of the universe without aging a single heartbeat. Imagine what it means for energy to travel without time. A photon cannot decay, cannot rust, cannot slow. It is eternal in a way matter can never be. And yet, when it meets an atom, it yields its energy instantly, transferring momentum, shifting the structure of electrons, sometimes even breaking bonds or forging new ones. This timeless traveler becomes part of a moment in your world, despite having no moments of its own. It is like a message in a bottle that was never written across time, only delivered. Niels Bohr and Werner Heisenberg wrestled with the implications of this quantum behavior. They saw that energy was not something carried like a physical object, but was entwined with fundamentally uncertain states of being. Heisenberg's uncertainty principle tells us that a photon's energy and time are linked in a relationship of probability. The shorter the time in which a measurement is made, the more uncertain the energy becomes, and vice versa. This delicate balance shapes how photons interact with atoms and molecules. In transitions measured in femtoseconds, energy can fluctuate within the narrow windows allowed by quantum rules, guiding processes like photosynthesis, vision, and even the chemical reactions in your own cells. Modern laboratories continue to explore these boundaries. At Fermilab, at DESY in Germany, and at KEIC in Japan, scientists use particle accelerators to study how photons transfer energy through interactions with electrons, quarks, and other elementary particles. In synchrotron light sources, gigantic rings where electrons race around near the speed of light, photons spill forth in controlled streams of X-rays. These X-rays allow researchers to map atomic structures, study materials, and observe biological molecules in motion. Each photon in these beams carries energy dictated by how tightly the electrons were curved by magnetic fields. No mass needed, only frequency. As you drift even deeper into the quiet space of your evening, consider the elegance with which Richard Feynman described the photon in his path, Integral Formulation of Quantum Mechanics. He suggested that a photon explores every possible path between 2 points, each path contributing a phase dependent on the action along that route. When all these possibilities interfere with one another, the most probable path emerges as what we observe. This idea, subtle and beautiful, describes how a photon can behave as both wave and particle, how it can carry energy across the universe without a single fixed trajectory. From this perspective, energy flows not because the photon is a tiny object pushing forward, but because the universe itself allows the field to explore configurations and settle into patterns consistent with the laws of probability. Imagine the space around you filled with these probabilistic fields, not empty, but alive with structure. The vacuum is not nothingness, but a sea of virtual particles flickering in and out of existence, suggested by the work of physicists like Paul Dirac, and later confirmed in experiments such as the Casimir effect. Even here, photons play a role, contributing to the shifting energy of the vacuum. These virtual photons, though they can never be detected directly, influence the forces between charged particles, adjusting the electromagnetic interactions in ways predicted by quantum electrodynamics. The equations written by Feynman, Julian Schwinger, and Shinichiro Tominaga reveal that the photon, even without mass, shapes the vacuum itself, altering the behavior of electrons with astonishing precision. The agreement between theory and experiment in QED is one of the most accurate in all of science, confirming the photon's role as a carrier of energy even in the absence of substance. And yet, you experience all of this in the simplest possible way, as light. When sunlight warms your arm, you feel the energy of photons absorbed by molecules in your skin. When you relax in a quiet room, the gentle glow from distant stars has traveled unimaginable distances to reach you. Those photons were born in nuclear furnaces, their energies carried outward through countless interactions, each step allowing them to shed a little frequency, a little momentum, until they reached the surface and fled across space. Their energy, transformed over vast epochs, now enters your eyes, stimulating delicate pigments in the retina. The phototransduction process that begins your act of seeing starts with a single photon rearranging the shape of a molecule called retinal. That tiny rearrangement triggers a cascade of electrical signals, bringing vision to life. A massless particle, through energy alone, opens the world to you. Scientists like Theodore Maiman, who built the first working laser, understood that coherent light, photons marching in lockstep, could carry not just energy but precision. Lasers now measure gravitational waves, cutting through space-time itself in detectors like LIGO and Virgo, where streams of photons bounce between mirrors miles apart. These photons, massless and tireless, reveal the subtle stretching of space-time caused by merging black holes billions of light-years away. They do so not with force or weight, but with frequency and phase, proving once again that energy can move mountains even when carried by something that weighs nothing at all. So, as you lie here, letting the world fall quiet, feel the presence of these unsung travelers all around you. They fill your room, glide past your skin, slip through glass, dance across the night sky. They shape your perception, your warmth, your sense of place. They flow from stars, from lamps, from the earliest moments of creation, each one a pulse of energy moving through the universe in perfect, weightless rhythm. The photon teaches you that energy does not require solidity. It requires only motion, and that sometimes the most powerful things in the universe are the ones that carry no weight at all. Even now, as your breath steadies into the quiet rhythm of the evening, you are surrounded by photons that were born in the earliest times of the universe. The cosmic microwave background, discovered by Arno Penzias and Robert Wilson in 1965, fills every direction of the night sky. These photons come from a moment when the universe first became transparent, when electrons and protons finally cooled enough to form neutral hydrogen. Before that moment, light could not travel. It scattered constantly in the dense plasma of the young cosmos. But when that fog lifted, photons streamed freely for the first time, carrying with them a snapshot of the infant universe. They have been traveling ever since, their wavelengths stretched by cosmic expansion until they now arrive as soft microwaves, weightless particles holding the memory of creation itself. The energy those photons carry has changed over billions of years. Their frequencies have lowered. Their temperatures have dropped from thousands of degrees to just above absolute zero. But their essence is still the same: ripples moving through the electromagnetic field, indifferent to mass, shaped instead by the curvature of space-time and the steady unfolding of cosmic history. Each one that reaches Earth today has crossed distances that defy comprehension, passing galaxies, drifting through voids, slipping along gravitational fields sculpted by dark matter. They have no mass to root them, no substance to slow them, so they follow space-time effortlessly, bending when space-time bends, turning when gravity guides their path. This bending of light, known as gravitational lensing, was first predicted by Einstein in 1915 and confirmed by Arthur Eddington's observations during a solar eclipse in 1919. Even though the photon has no mass, the path it takes curves around massive objects because gravity is not a force acting on mass. It is the geometry of space-time itself. When starlight passes near a galaxy cluster, it stretches into arcs and rings, revealing structures too faint to see otherwise. Telescopes like Hubble and now JWST use this effect to peer into the deep past, studying galaxies from the early universe. In every distorted image, photons reveal their story, massless travelers obedient to the curvature of existence. They carry energy across billions of light years, but they do so along paths written by gravity's hand. You can imagine space-time as a vast ocean, not of matter, but of geometry. A photon does not swim through this ocean. It simply flows along the shape of the waves. Because it has no mass, it cannot push back against the curvature. It cannot choose a straight line when space itself curves. It surrenders entirely, and in that surrender, it unveils the invisible structure of the cosmos. Astronomers use these distortions to map dark matter, which neither emits nor absorbs light. They see its effects only in the bending of photon paths. Thus, the photon, though weightless, becomes a detective of the unseen, revealing the hidden scaffolding of reality. And yet, while photons glide effortlessly through space, they interact with matter in exquisitely sensitive ways. When a photon encounters an electron bound within an atom, a delicate negotiation occurs. If the photon's energy matches the gap between two electron energy levels, the electron can absorb the photon, leaping to a higher state. This resonance condition is why atoms absorb specific colors of light, giving each element its unique spectral fingerprint. It was through studying these spectral lines that Niels Bohr crafted his model of the hydrogen atom, proposing discrete energy levels that later inspired the foundations of quantum theory. A massless particle, carrying energy in its frequency alone, guided us to the first understanding of quantized atomic structure. These interactions shape the world you see. The green of leaves arises because chlorophyll molecules absorb red and blue photons while reflecting green. The deep reds of sunset occur because long wavelength photons scatter less in the atmosphere, while shorter blue wavelengths scatter more, painting the sky in gradients of color as the sun descends. Every hue around you is a direct conversation between photons and electrons, an exchange of energy without mass, sculpting vision itself. The human eye is a masterpiece of photon sensitivity. Photoreceptors in your retina, rods, and cones contain molecules of retinal bound to opsins. When a single photon strikes a retinal molecule, it changes shape from a bent form to a straight one. This minuscule shift triggers a biological cascade that amplifies the signal, ultimately forming a nerve impulse. Astonishingly, your eye can detect the arrival of a single photon. Weightless, timeless, but carrying enough energy in its frequency to transform a molecule and spark perception. Your experience of the world begins with these tiny transformations, moment by moment, photon by photon. In laboratories, scientists measure the energy of photons with extraordinary precision. Experiments at NIST use cryogenic detectors cooled to near absolute zero to capture single photons and measure their energies through the heat they deposit. At SLAC, researchers accelerate electrons to nearly the speed of light and force them through magnetic undulators, producing intense beams of X-rays, where each photon's energy reveals details of molecular structures and electronic states. At CERN, experiments study photon-photon collisions, rare but incredibly informative events where light interacts with light through quantum field processes, mediated by virtual particles flickering into existence. These experiments confirm predictions from quantum electrodynamics with astonishing precision, sometimes to more than 10 significant figures. No theory in the history of science has matched reality as closely as QED, and the photon is its central actor. Yet the photon remains mysterious. What does it truly mean for a particle to have no rest mass? What does it mean for it to travel at the speed of light not as a choice, but as a requirement? In special relativity, the speed of light is not simply fast. It is the boundary between two domains of reality, one for massive particles, which move slower than light, and one for massless particles, which must move at this speed. Mass slows motion by requiring energy to accelerate, but a massless particle has no such burden. It is pure motion, woven into the geometry of space-time. When physicists like Hermann Minkowski unified space and time into a four-dimensional continuum, they saw that the world line of a photon lies along what is called a null interval, an interval with zero proper time. For a photon, no time elapses. No distance is experienced. In its own frame, the entire universe is compressed into a single moment, a single point of contact between emission and absorption. And yet, from your perspective, that same photon may have traveled billions of years to reach you. These two truths coexist, not contradicting but complementing one another. The universe allows different observers to carry different measures of time, depending on how they move through space-time. And the photon, unable to slow, is the ultimate outsider to the flow of time. Even now, as you sink deeper into the calm, imagine the quiet simplicity of this idea. A photon is created when an electron drops to a lower energy level, releasing energy. That energy becomes a vibration. That vibration becomes a wave. And the wave becomes a quantized packet that travels across the universe until it meets something capable of absorbing it. There is no mass to weigh it down, no internal structure to complicate its journey, only the pure resonance of a trembling field. Scientists like John Wheeler once asked whether the universe might be fundamentally built from bits of information. In that view, the photon becomes a messenger not just of energy but of knowledge. Knowledge of transitions, collisions, temperatures, histories. When a photon reaches you, it tells you where it came from, how far it has traveled, and what interactions it has survived. It carries the imprint of ancient stars and distant quasars. It carries the fingerprint of the cosmic beginning. It even carries the subtle distortions of gravitational waves passing through space-time. In this way, the photon is both silent and eloquent, weightless but profound. Your body, too, speaks in photons. Every moment, infrared photons radiate from your skin as heat. This radiation is not wasteful. It is the natural release of energy into the environment. Night vision cameras detect these photons, each one whispering the temperature of your skin. The universe is constantly exchanging energy through these weightless particles, a quiet dialogue between all warm things and the cold deepness of space. And when you inhale softly in the dark, the warmth you feel inside your chest is partly the result of photons interacting with the molecules of the air and the tissues within you. Energy moves gently through the world, shaping matter, guiding chemistry, igniting the processes that sustain life. Photons, with no mass of their own, are among the most essential carriers of that energy. There is an elegance in the way physics allows energy to exist without substance. It means motion can be fundamental. It means rhythm can be real. It means that something can change the universe simply by changing its frequency. And so, as the night deepens around you, feel the presence of these ancient travelers. They move through walls, through windows, through the spaces between atoms. They dance across your room, weaving the patterns of shadow and glow. They carry the warmth of the day into the coolness of the evening. They carry the memories of stars into the gentle quiet where you are now. Their weightlessness is not a lack, it is a freedom from time, from rest, from decay. The photon is the universe in motion, distilled to its purest form. And the energy it carries is the heartbeat of everything you see, everything you feel, everything illuminated within and around you. And so the photon moves through you, around you, beyond you, a constant reminder that energy is not confined to mass, that the universe has ways of carrying its messages that transcend the rules you sense in your everyday life. As your thoughts drift gently toward the quieter edges of awareness, picture the simplicity and the strange richness of that truth. A photon contains no matter, yet it carries the power to shift electrons, drive chemical reactions, and even create life. Plants depend on photons for photosynthesis, a process unraveled by scientists like Robert Emerson and Otto Warburg, who identified the wavelength sensitivities that determine how chlorophyll absorbs energy. When a photon strikes the reaction center of a photosynthetic complex, it transfers its entire energy in a single instant, launching electrons into pathways that ultimately build sugars from carbon dioxide. A massless particle powers the foundation of Earth's ecosystems. Its energy, held solely in frequency, becomes the fuel for forests, oceans, fields, and the quiet breath rising and falling within you. This same idea extends beyond biology into the far reaches of astrophysics. When researchers at the European Southern Observatory study star-forming regions like the Orion Nebula, they observe ultraviolet photons stripping electrons from hydrogen atoms, carving out vast cavities in interstellar gas. These photons sculpt star nurseries, shaping the birthplaces of future suns. They carry energy without mass, yet they reshape entire landscapes of gas and dust, altering the conditions under which new stars ignite. The photon becomes a kind of cosmic gardener, pruning and guiding celestial structures across millions of years. Far from the liveliness of star-forming regions, photons also mark the final breaths of dying stars. When a white dwarf accumulates material beyond a certain threshold, it can ignite in a type Ia supernova, releasing photons across the electromagnetic spectrum. These explosions are so luminous and so uniform that astronomers use them as standard candles to measure cosmic distances. In the late 1990s, teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees discovered from these supernova observations that the universe's expansion is accelerating, driven by something now called dark energy. The clues came from photons traveling billions of years through an expanding cosmos, bringing with them the story of distant cataclysms and the gentle, relentless swelling of space-time. Without mass, these photons carried the evidence that the universe is far stranger than once believed. And still, even while photons illuminate the vast structures of the cosmos, they remain intimately woven into the smallest corners of your own physics. The energy levels of atoms, mapped in exquisite detail through spectroscopy, reveal themselves only when photons interact with electrons. Precision measurements of hydrogen's spectral lines, such as the 21-centimeter line arising from electron-proton spin flipping, allow astronomers to observe cold hydrogen gas in distant galaxies. Every spectral peak, every absorption trough, every fluorescence pattern is a signature of photon interaction, telling us how energy flows through matter at the smallest scales. Photons do not need mass to carry this energy. The shape of their wave, the pace of their oscillation does all the work. When scientists at Gila in Colorado developed optical lattice clocks, devices so sensitive that they lose or gain less than 1 second over the age of the universe. They relied on photons interacting with atoms in exquisitely controlled ways. These clocks use lasers tuned to specific frequencies so that photons can excite electrons with extraordinary precision. The energy of each photon is so well defined that it becomes a measure of time itself. Timekeeping, in this modern form, is a dialogue between massless particles and bound electrons. The stability of these photons allows us to refine GPS systems, synchronize communication networks, and probe the subtle warping of spacetime predicted by general relativity. Again, no mass is needed, only frequency, only rhythm, only the uninterrupted pulse of light. Let yourself feel the strange serenity in this idea. The universe uses rhythm to measure itself. Photons, moving at the speed of light, define the metric by which distances and times are described. When physicists talk about the speed of light, they are not describing how fast a particle moves through empty space. They are describing the structure of space-time itself, because the photon is not moving through something external. It is following the very rules by which reality bends, stretches, and evolves. To say that the photon has no mass is not to diminish it. It is to recognize that it is more deeply connected to the architecture of the universe than massive particles could ever be. Massive particles must negotiate with inertia. They must trade energy for acceleration. They must experience time's flow. But photons glide along the most fundamental pathways of space-time, slipping from one event to another without tasting duration. This is why they carry energy so effortlessly. They are not burdened by rest. They do not require kinetic reservoirs or internal storage. Their energy is encoded in their frequency, and the universe preserves that frequency, or stretches it gently, depending on the curvature and expansion of space-time. Think of Edwin Hubble watching galaxies drift apart. He did not touch those galaxies. He measured the redshift of their light, the stretching of the photons arriving from distant stars. The galaxies did not need to tell him they were receding. The photons told him, simply by having lower frequencies than when they left their sources. The energy carried by those photons had softened, lengthened, relaxed across billions of years of cosmic expansion. And in that relaxation, they revealed the motion of entire galaxies, massless particles, carrying the information of cosmic motion in nothing but the pace of their trembling. Even now, photons carry the signatures of exoplanets hidden around distant stars. The slight dimming detected by missions like Kepler and TESS comes from photons being blocked or scattered as a planet transits. The wobble in a star's spectral lines, caused by the gravitational influence of an orbiting planet, is detected through shifts in photon frequency. Every discovery in modern astronomy is, in one way or another, a conversation with photons. They whisper secrets from across the universe, delivering messages that began long before you were born. Messages that come wrapped not in mass, but in the pure geometry of energy. And at the foundation of all this lies the simple truth. A photon is not a particle in the classical sense. It is not a tiny bead flying through emptiness. It is a quantized excitation of the electromagnetic field. When that field vibrates in the right way, the vibration can travel, and that traveling vibration is the photon. Its energy is the measure of how quickly the field oscillates. Its momentum is a consequence of its motion through space-time. It carries no mass because mass is not required for it to exist. Instead, it is born of relationships, of changes, of transitions. It is the embodied difference between two states of matter, and the vehicle that delivers that difference to the rest of the universe. As you rest more deeply, feel how soft and inevitable this becomes. Energy moves constantly through the cosmos, flowing from stars to planets, from atoms to molecules, from galaxies to telescopes, from lamps to your skin. And photons are the vessels of that movement. They are the purest expression of what energy can be when freed from the weight of matter. They do not ask for rest. They do not tire. They do not age. They exist only in motion, and in that motion, they carry the warmth of suns, the colors of landscapes, the memories of creation, the structure of atoms, and the shape of time itself. And as the quiet thickens around you, you may begin to sense that photons are not separate from you. Every cell in your body absorbs and emits them. Every thought you have relies on electrical activity that in turn can release weak photons. The biophoton studies of researchers like Fritz Albert Popp, though controversial in their interpretations, suggest that living systems might use extremely faint light emissions in ways not yet fully understood. Whether or not these ideas survive the scrutiny of modern physics, they remind us that life and light have always been intertwined. Photons do not merely illuminate life, they participate in it, becoming part of its subtle rhythms. So, as your mind settles, as the world grows dimmer and softer, you can imagine yourself suspended in a sea of these weightless travelers, each one a quanta of energy, each one a whisper of motion, each one a vibration encoded with purpose but free of mass. You exist within their glow, their warmth, their stories. They pass through the atmosphere, through glass, through space, through time, all without losing their essential simplicity. They teach you that energy, true energy, does not need solidity to be real. It can exist in rhythm, in frequency, in the shimmering boundaries between fields. And in this sea of motion without mass, you begin to sense how the photon is not merely a tool of physics, but a thread that stitches the cosmos together. Every interaction that shapes your world, from the glowing edges of a sunrise to the faint glimmer of distant galaxies, depends on the ability of photons to carry energy across space without ever slowing, without ever acquiring weight. They belong to a category of beings that live in the boundary between what is here and what is not, between presence and possibility. Physicists like Leon Lederman once remarked that light is the messenger of the gods, not as a metaphor of myth, but as a recognition that photons transmit the universe's deepest truths to anyone who knows how to read them. When telescopes like JWST open their mirrors to the night, they are not capturing images in the conventional sense. They are interpreting the arrival of photons that left their sources billions of years ago. These photons encode the temperature, composition, and velocity of ancient stars, allowing astronomers to reconstruct the earliest chapters of cosmic history. No mass is needed for this story to cross time. Only frequency, only phase, only the quiet endurance of vibration. Even the structure of matter is revealed by photons. The famed scattering experiments conducted by Ernest Rutherford in the early 1900s used alpha particles to probe the nucleus, but later experiments like Compton scattering relied on photons to unveil the momentum and binding energies of electrons. In Compton's 1923 experiment, X-ray photons collided with electrons, and the shift in their wavelengths revealed the particle-like momentum of light. This discovery earned Arthur Compton the Nobel Prize and cemented the idea that photons, though massless, carry momentum that behaves as though it were tied to mass, but without the burden of mass itself. They move, push, nudge, repulse, and interact with a touch so delicate it can rearrange atoms. And that delicate touch shapes every technological wonder around you. Fiber optic cables, for example, guide photons through slender strands of glass with minimal loss. They bend and weave through the world beneath sidewalks, oceans, and city grids, carrying vast rivers of information. The entire internet, in its deepest layers, is a choreography of massless particles, reflecting and refracting along glass corridors. Each photon emerges from a laser diode, carrying bits of data encoded in its phase, amplitude, or polarization. That data travels almost at light speed, slowed only slightly by the refractive index of the medium. From continent to continent, photons whisper the digital heartbeat of human civilization. Inside quantum computing research labs, photons are now being explored as qubits, units of quantum information. Because photons do not interact strongly with each other, they can preserve quantum states over long distances, making them excellent carriers for quantum communication. Researchers at the University of Science and Technology of China demonstrated quantum teleportation over more than 1,000 kilometers using entangled photons. These entangled particles remain correlated across vast distances, responding as one system even when separated by mountains, lakes, or orbiting satellites. Their masslessness does not hinder their ability to encode profound structures of quantum information. If anything, it makes them ideal, free of inertia, free of decay, free to glide through the quiet fabric of the world with states intact. In these experiments, the photon reveals another astonishing trait. It can exist in superposition, traveling many paths simultaneously, encoding multiple possible realities until interaction collapses the wave function. This is not metaphor. It is one of the most thoroughly tested predictions of quantum mechanics, confirmed in countless interferometry experiments. From early Michelson-Morley setups to modern quantum optical circuits etched onto chips no larger than your thumbnail. The photon's path, undefined until observed, is a reminder that energy unfolds in possibilities rather than certainties. And yet, those possibilities carry real power. When the photon finally interacts, all its potential collapses into a single transfer of energy, precise and irreversible. Let your mind drift to the boundary of classical and quantum behavior, where experiments such as the Hong-U-Mandel effect show how two identical photons entering a beam splitter can exit together, their probability waves interfering in such a way that the universe forbids them from taking different paths. This gentle effect, discovered in 1987 by Chung-Ki Hong, Jae-Yu Wu, and Leonard Mandel, reveals the deep symmetry embedded in the laws of nature. Two massless particles, carrying nothing but frequency and phase, synchronize their destinies without ever touching, guided only by the mathematics of bosonic fields. Even more quietly, in the hearts of stars, photons enact the slow, patient work of transporting energy from nuclear reactions outward through dense layers of plasma. In the sun's core, gamma-ray photons born from fusion take thousands to millions of years to reach the surface, bouncing from particle to particle in a random walk so intricate that their energy is gradually transformed into visible light. When the sunlight touches your skin, you are feeling the surface echo of a photon's long, wandering journey. A journey that began long before any human existed to witness it. And yet the photon that finally reaches you is new, freshly emitted from the solar surface. But its lineage traces back to a long history of interactions, equilibrations, and transformations. Its energy traveled through eons to find you here, tonight, resting in the quiet. In laboratories studying quantum electrodynamics, such as those where Hans Dehmelt and Wolfgang Paul refined the trapping and measurement of single electrons, researchers have observed that the electron's mass and charge are subtly altered by interactions with the sea of virtual photons that fill the vacuum. This process, called renormalization, shows that even empty space hums with electromagnetic activity. Photons flicker in and out of existence, influencing charged particles in subtle ways. Even in the void, photons shape the behavior of matter. Their massless nature allows them to respond instantly to disturbances in the field, forming a background of activity that is always present, always dynamic, always capable of carrying energy even when no real photons are being observed. As your breath softens, consider what this means for the very concept of matter. The photon, though weightless, is responsible for nearly every interaction you experience. The solidity of a chair arises from electromagnetic repulsion between electrons in the chair and electrons in your body. That repulsion is mediated by photons, virtual photons exchanged at unimaginable rates. When you touch something, you never truly make contact in the classical sense. Instead, the electromagnetic field pushes back through a cloud of exchanged photons. Touch, solidity, texture, all are manifestations of interactions carried by particles that weigh nothing. And because photons move at the speed of light, they define the horizon of what is possible. Nothing with mass can catch up to them. Nothing can outrun them. Nothing can transmit information faster than they can. They are the universe's limit and its messenger, a balance point between motion and stillness. Their masslessness is not a flaw or a lack, but an essential symmetry. It keeps the structure of physics coherent. If photons had even a small mass, the electromagnetic field would behave differently. Light would not reach infinitely far. Coulomb's law would decay. Atoms would not be stable in their familiar forms. Chemistry, as you know it, would unravel. The weightlessness of the photon is not an accident. It is a condition that allows the universe to exist in its present, elegant form. Let yourself sink deeper into that thought. Massless light shapes massive reality. Weightless motion defines weighty worlds. A rhythm without substance builds the textures, colors, and contours of your experience. When you look at a candle flame, the warm glow is a stream of photons emitted by excited atoms returning to lower energy states. When you gaze at the stars, each spark of light is a river of photons traveling across time, carrying with them stories older than Earth. Even the darkness between those stars is filled with low-energy photons from ancient cosmic epochs, stretched into near silence. You exist in a universe bathed in these messengers, and you yourself radiate them continuously. A human body at rest emits infrared photons, each one carrying away a tiny piece of thermal energy. This is how your warmth reaches the air, how your body cools in a gentle room. It is a process so subtle you rarely notice it, yet it is present in every moment of your life. Energy leaving you in weightless packets. Energy arriving in weightless packets. A cycle that never ends. And, as you settle more deeply into this calm, the insight begins to feel natural, effortless. Energy does not require mass. It flows through frequencies, through waves, through fields. The photon is simply the universe's purest expression of that truth. It is not a thing, but a happening. Not an object, but a movement. Not a body, but a change. When you close your eyes, photons still touch your skin, warming you gently, reminding you that even in darkness, energy continues to travel. And all the while, as you move deeper into this gentle space, the presence of photons around you begins to feel less like an abstract concept and more like the quiet structure of your reality. Every surface that reflects the faintest glimmer is doing so by releasing photons. Every shadow is a place where photons could have gone, but didn't. Every warm breath leaving your chest carries its own spectrum of infrared light. A soft glow invisible to your eyes, but perfectly real to the mathematics of thermodynamics. And the energy of those photons, though they weigh nothing, plays into the balance of heat and movement in the world around you. This subtle truth has been measured in some of the most sensitive experiments ever built. When scientists at MIT constructed ultra-cold atom traps, bringing matter close to absolute zero, they found that stray photons, just a few gentle excitations of the electromagnetic field, could heat the atoms enough to disrupt the formation of delicate quantum states. In these frigid laboratories, a single photon can shift the fate of thousands of atoms. In rooms so cold that matter behaves like waves, the arrival of a photon is like the quiet footstep of a giant. It doesn't need mass to make an impact. It needs only the energy hidden in its frequency. Even in cosmic voids, photons leave their mark. High-energy gamma rays traveling through intergalactic space interact with background photons from the cosmic microwave background and the extragalactic light field. These interactions can create electron-positron pairs, gradually softening the gamma-ray energy. Observatories like Fermi-Lat and ground-based Cherenkov telescopes watch these high-energy photons arrive from distant blazars, their energies attenuated by journeys spanning billions of years. From these patterns, scientists reconstruct the density of diffuse light in the universe. Light too faint to see directly, but detectable through the whispers it leaves in the energy of passing photons. No mass is required for these conversations across cosmic distance. Only the gentle arithmetic of fields and frequencies. As your thoughts soften, notice how photons act not only as carriers of energy but as diplomats between realms of scale. they speak equally well with the smallest particles and the largest structures. A photon can shift the spin of a lone electron or reveal the swirling arms of a distant galaxy. It can trigger a biochemical reaction in your retina or outline the silhouette of a black hole's event horizon. When the Event Horizon Telescope captured the first image of a black hole in 2019, it did so by measuring the millimeter wavelength photons that had skimmed the edge of the accretion disk, bent and twisted by the gravitational well before their long journey to Earth. Those photons, though weightless, traced the outline of a gravitational monster so dense that not even light could escape from its center. The image was not a photograph of the black hole itself, but a map of the dance of photons around its edges. The energy carried by those photons revealed a place where energy and geometry merge in the most extreme way known. And the strangeness of the photon goes even deeper. In high-energy physics, photon interactions hint that the vacuum is not empty, but populated by fields that shift and respond to momentum and frequency. When photons scatter off each other in photon-photon interactions, something once thought impossible, they do so through virtual particles like electron-positron pairs, appearing for fleeting intervals allowed by Heisenberg's uncertainty principle. Experiments at the Large Hadron Collider have observed these rare scattering events in ultra-peripheral heavy-ion collisions, confirming predictions of quantum electrodynamics made decades earlier. Even though photons carry no mass, their energy is enough to shake the vacuum and reveal its hidden layers. Energy alone, encoded in frequency, can unlock the secrets of the quantum world. And yet, even with all these remarkable roles, the photon remains breathtakingly simple. It does not decay. It does not age. It does not change its internal structure, because it has none. Its existence is defined entirely by motion and vibration. If you remove motion from a photon, it no longer exists. If you slow it, it ceases to be a photon and becomes a static electromagnetic field. It is a creature of pure momentum, a ripple that cannot stand still. In this way, the photon teaches you something profound about the universe. That motion can be a kind of being. That existence does not always require substance. That sometimes what matters most is not what something is made of, but what it does, how it moves, how it interacts, how it shares its energy with the world. You might imagine now, in the dim quiet around you, how many photons have passed through your life. The photons from the first sunrise you ever saw. The photons from the candles on childhood birthdays. The photons that glinted off the eyes of someone you loved. All of them carried energy without mass. All of them arrived at your senses as gentle rearrangements of electrons, tiny transfers of frequency that became memories in your mind. And even memories, in their way, are shaped by light. Neural activity is electrical, and electricity is tied to electromagnetic interactions. At the smallest scales, your thoughts are intertwined with photons. Virtual photons exchanged between charged particles in your neurons. These virtual photons, though they do not travel like real ones, still mediate the forces that build your experiences, shape your emotions, hold your identity in place. The weightless architectures of light help hold together the weight of your world. In the vast field of cosmology, researchers studying the early universe, such as those working with the Planck satellite or the South Pole telescope, use photons to trace the earliest ripples in density that later grew into galaxies and clusters. These primordial temperature variations, imprinted on the cosmic microwave background, reveal the shape of the universe when it was only a fraction of a second old. The energy carried by those ancient photons holds information about inflation, the rapid expansion theorized by Alan Guth and André Linde. Though photons have no mass, their energy encodes the fingerprints of forces far more powerful and ancient than anything seen in the modern cosmos. Through them, the universe remembers its own beginning. And as you drift further inward, you may sense that the photon occupies a kind of boundary between reality as you know it and the deeper structure beneath. It acts like a translator, fluent in both the language of quantum uncertainty and the language of classical experience. It can behave as a wave spread across space, and at the moment of interaction, it behaves as if it were localized to a single point. This dual nature puzzled Einstein, troubled Bohr, fascinated Feynman, and still inspires researchers today. But it is not contradiction, it is completeness. The photon is not choosing one form or another. It is expressing the richness of a universe where energy and information are woven through probability. This same idea underlies the field of quantum optics, where scientists like Alain Aspect and Anton Zeilinger demonstrated the reality of entanglement. Photons linked across distance in ways that defy classical intuition. When two entangled photons are created, measuring the state of one instantly determines the state of the other, no matter how far apart they are. This does not allow communication faster than light, but it shows that photons share connections deeper than space alone. Their energy and quantum states hold correlations that stretch across separation, like threads tying distant points together. For this work, Aspect, Zeilinger, and John Clauser were awarded the Nobel Prize in 2022, solidifying the photon's role not just as a carrier of energy, but as a carrier of correlation, coherence, and the subtle logic of quantum information. And so, the weightless particle that warms your face, powers your screens, paints sunsets, and carries the memories of galaxies is also a bridge into the quantum structure of reality. Its energy, held entirely in frequency, flows effortlessly between the classical and quantum realms. A photon can behave like a wave expanding across kilometers, or like a single event shifting a molecule in your eye. It can encode vast, astronomical distances or whisper through the smallest biological reaction. And in each expression, it remains the same: massless, timeless, tireless. And the more you settle into this gentle rhythm, the more you begin to feel how photons are not merely particles that pass through your world. They are the architecture of everything you perceive. You do not simply see with light. You live inside a universe shaped entirely by its presence. Every horizon you've ever observed, every texture, every glimmer, every soft edge of morning or late-night glow has reached you through photons that traveled vast distances or emerged from intimate depths of matter. Their weightlessness does not diminish their reach, it amplifies it. For without mass, they can cross the cosmos without resistance, without decay, without ever tiring. They are the most persistent travelers the universe has ever known. In the realm of plasma physics, photons guide the behavior of matter so hot that electrons and nuclei move freely, forming the most common state of matter in the visible universe. Research at facilities like the National Ignition Facility reveals how photons can trap themselves inside hot plasma, scattering relentlessly until they diffuse outward. In stars like the Sun, this photon diffusion shapes the outward flow of energy, regulating the star's stability. Without photons moving through this plasma, stars would collapse under their own gravity or explode from internal pressure. So, even as they weigh nothing, photons uphold the balance that allows stars to burn gently rather than catastrophically. They carry energy outward like a slow pulse, smoothing the violent heart of fusion into something steady enough to warm planets and nourish life. This diffusion is not a simple journey. Deep inside a star, a photon is absorbed and re-emitted countless times before emerging at the surface. Each absorption transfers energy to the plasma, and each re-emission creates a new photon with slightly adjusted frequency. In this long chain of interactions, the photon becomes a part of the internal dialogue of a star, communicating energy across layers of plasma that behave like living surfaces, constantly shifting and folding. And when the final photon escapes into space, it carries within its frequency a story that began in the core of a star ages before. Its massless form is filled with the gentle echo of nuclear fire, delivered softly across 93 million miles to the Earth, where it glances across your skin with warmth. And these stellar photons do more than warm. They guide the growth of worlds. In the early solar nebula, photons from the forming sun pushed lighter gas outward, shaping the architecture of the solar system. The giant planets formed far from the star, while rocky planets like Earth formed closer in the regions where heavier elements settled. Photons sculpted these regions through radiation pressure, sorting dust and gas into structures that later condensed into planets, moons, and comets. Even the shadowy asteroid belts owe some of their form to the push of solar photons nudging particles into stable resonances. This subtle guiding hand is not often felt in daily life, but it is recorded in every orbit of every world around the sun. And long before planets were born, long before stars themselves ignited, photons played another role. During the era of recombination, when electrons and protons first combined to form stable hydrogen, photons shifted from a state of constant scattering to a state of free travel. In that moment, the universe transitioned from opacity to transparency. The cosmic microwave background, measured with exquisite precision by the Planck satellite and earlier by COBE and WMAP, is a snapshot of those very photons. They have traveled nearly 14 billion years to reach us, their wavelengths stretched by cosmic expansion into microwaves, yet still carrying the signature of density fluctuations that would grow into galaxies and clusters. These photons, gentle and ancient, deliver the fossilized imprint of a time before stars, before planets, before any structure had taken form. Without mass, they have held this memory perfectly intact, untouched by time. Feel how extraordinary that is. Something weightless, something that cannot slow or rest, has carried the history of the universe across its entire lifetime, and you are receiving it in the quiet of your room this very moment. The energy of those photons is faint, just a whisper above absolute zero, but their presence fills all of space. They drift through walls, through bodies, through cities, through mountains. A constant cosmic glow, invisible yet undeniable, bathing everything in existence with a memory older than any atom in your body. And this memory is encoded in frequency, the same simple rhythm that defines every photon, from the brightest gamma ray to the softest radio wave. Even black holes, the darkest places in the universe, express themselves through photons. The Hawking radiation predicted by Stephen Hawking arises from quantum fluctuations near the event horizon. In that delicate interplay, particle-antiparticle pairs flicker into existence. Sometimes one falls into the black hole while the other escapes as radiation. The escaping particle is often described as a photon, carrying with it a sliver of energy extracted from the gravitational field. Hawking radiation has never been observed directly, but its theoretical implications are profound. Even the most massive, light-swallowing objects in the universe ultimately speak through photons. They lose energy in the form of massless radiation, dissolving their darkness into waves of pure frequency over unimaginable spans of time. And the universe listens. Instruments on Earth and in orbit watch for photons that carry clues to fundamental physics. Experiments like the Pierre Auger Observatory study ultra-high-energy cosmic rays that produce cascades of energetic photons when they strike the atmosphere. X-ray telescopes like Chandra and NuSTAR reveal the violent regions around black holes and neutron stars. Gamma-ray telescopes like HESS, MAGIC, and Veritas observe the extreme energies emerging from supernova remnants, pulsars, and active galactic nuclei. And through all of these observations, one truth persists. Photons are the cosmic couriers that reveal what matter alone cannot. Even the most violent and distant events speak to us through weightless light. And, as the night folds deeper around you, another gentle realization emerges. Photons shape the boundaries of what you can know. Everything you see depends on how photons interact with the world. Everything you don't see depends on where they cannot go. Your visual system, your memories of landscapes and faces, your sense of color and shadow, all arise from the way photons scatter, absorb, and reflect. Entire fields of physics and astronomy rely on these behaviors, yet at their heart lies the same simple mechanism: energy carried by vibration. When astronauts aboard the International Space Station watch lightning storms on Earth, they see them as bursts of photons rising through the atmosphere. When volcanologists measure lava temperatures, they analyze the infrared photons emitted by molten rock. When medical imaging devices peer inside the human body, PET scans, CT scans, X-rays, they rely on photons to reveal structures hidden beneath skin and bone. Even the warmth you feel when sitting near a campfire is carried by photons that began in the chaotic combustion of wood fibers, leaping into the night as waves of infrared light, journeying toward you without weight, without resistance. And in all of this, a thought rises gently. The photon does not belong to any one scale. It belongs to all of them. It serves the smallest biochemical reaction and the largest cosmic event with the same quiet neutrality. It is the bridge between your perception and the universe's unfolding story. Every photon carries energy because frequency is its language, and frequency needs no mass to be real. Light does not need weight to move you, to warm you, to guide you, to reveal the shape of the cosmos. And the deeper your breath becomes, the clearer this truth begins to feel, not as an intellectual idea, but as something woven into the quiet spaces of your awareness. You begin to sense how every photon that touches you has traveled through a reality far more subtle than the one you hold in your waking thoughts. A reality shaped by fields intertwined with the vacuum, by quantum rules that dissolve the boundaries between possibilities, by geometries that bend around gravity, by an expansion that stretches even the fabric of motion itself. And through all of that, through every transformation, through every interaction, through every cosmic distance, the photon carries energy without mass because it is that energy. A pulse of existence crossing the void, a tremor in the fabric that needs no body to carry it. a ripple that endures across time without ever experiencing time. And as you drift deeper into this gentle current of thought, you begin to realize that photons are not merely carriers of energy. They are carriers of boundaries, shaping what you can experience and what remains forever unseen. When ultraviolet light from the sun is absorbed by the ozone layer, it is photons that deliver the energy to break molecular bonds, creating the chemical cycles that shield life on Earth. When cosmic rays strike the upper atmosphere, they generate showers of photons that cascade downward in brilliant chains of particle interactions. When auroras shimmer across polar skies, it is the energy of solar photons, first stored in charged particles, then released again in glowing ribbons, that paints the night with gentle flowing light. Even the stars themselves depend on photons for their stability. Deep inside the sun, the outward pressure generated by photons bouncing through the plasma balances the gravitational pull trying to collapse the star inward. This balance, known as hydrostatic equilibrium, is why stars neither collapse nor explode during most of their lifetimes. The photons provide just enough outward influence to hold gravity at bay. Massless particles resisting the inward pull of a mass 1,000,000 times greater than Earth. It is a quiet, patient resistance, unfolding over billions of years, and yet it keeps the star in a state of delicate harmony. And from that harmony comes the warmth that allowed Earth to blossom. The photons arriving on Earth carry not only energy but information about the nuclear reactions in the solar core. By analyzing the spectrum of sunlight, scientists can determine the temperature of the solar photosphere, the composition of the outer layers, even the motion of sunspots drifting across its surface. Each photon holds a signature of the journey it has taken, shaped by countless interactions. It travels as a wave, but at the moment it touches your skin, it behaves as if it were a single particle delivering a precise packet of energy. This dual behavior is not contradiction, but completeness. An understanding first clarified by the pioneers of quantum theory who saw that nature speaks both languages at once. Louis de Broglie proposed that all particles have wave-like properties, and photons, though massless, sit at the heart of that insight. Their wavelengths and frequencies are not merely characteristics. They define how photons behave, how they interfere, how they diffract around edges or pass through narrow slits. In elegant experiments by Geoffrey Taylor in the early 20th century, even a single photon passed through a double-slit apparatus created a faint interference pattern when repeated many times. This showed that the wave nature of photons persists even when they arrive one by one. Probability itself becomes the medium through which they travel. And in that medium, the photon's energy is distributed as a wave, yet delivered as a particle. Let your thoughts soften into that paradox. A photon is not confined to a single trajectory until it interacts. Before absorption, it expands through space as a wave of possibility. Once absorbed, it appears as if it had always followed a single path. Researchers working with quantum optics, like Serge Haroche, who isolated individual photons in microwave cavities, have shown that even a trapped photon can exhibit quantum behavior so subtle that its presence changes the resonant structure of the cavity without the photon ever being absorbed. Its energy, held in vibration, shifts the behavior of the field itself. This sensitivity becomes even more striking in phenomena like Raman scattering, where photons interact with molecules and gain or lose small amounts of energy, revealing vibrational modes that characterize chemical bonds. Through careful measurements of these scattered photons, scientists identify the composition of materials, from ancient pigments in artwork to the molecular signatures of biological tissues. The energy carried by these photons is so slight, yet so precise, that it opens windows into the microscopic world without ever touching it directly. Weightless energy unveiling structure through frequency alone. And when you breathe in the calm of this moment, you may begin to sense how deeply photons influence your own rhythms. The circadian clock within your brain, centered in the suprachiasmatic nucleus, is regulated by blue wavelength photons that signal day and night through specialized retinal cells. These cells, discovered by David Berson's team in the early 2000s, respond specifically to light levels and send that information to the brain's internal timing system. Photons, not mass, not pressure, not sound, tell your body when to wake, when to sleep, when to release hormones that guide your internal tides. Your daily cycle is choreographed by weightless particles that touch your eyes with the gentlest whisper of energy. Even more quietly, in the quantum biology of your own body, photons may play roles still not fully understood. Experiments in avian navigation, for instance, suggest that some animals sense Earth's magnetic field through quantum processes involving entangled electrons, processes potentially influenced by photon absorption within cryptochrome molecules. While the exact details remain under active study, these findings hint that life itself may depend on delicate quantum interactions shaped by the way photons trigger molecular reactions. And though humans do not navigate by magnetic fields, the same molecules exist in your body, responding to light in ways that influence mood, alertness, and internal balance. Consider, too, how photons guide the architecture of matter itself. When electrons in atoms absorb photons, they jump to higher orbitals, and when they release photons, they fall back down. The structure of molecules, the shapes they adopt, the bonds they form, all of these depend on how electrons move, and electrons move in response to photons. The geometry of your DNA, the structure of proteins, the behavior of enzymes, every one of these is tied to the quantum transitions that photons drive. The energy of light shapes the architecture of life from the inside out. And, as your awareness sinks deeper into this subtle truth, another thought takes shape. Photons do not merely traverse space, they define the very geometry by which space is measured. When physicists measure distances using interferometers, such as those in LIGO, Virgo, or the upcoming LISA mission, they rely on the phase of photons traveling along long arms of vacuum. The interference patterns created by these photons reveal shifts smaller than 1,000th of a proton's width, caused by gravitational waves rippling through space-time. These waves stretch and compress space itself, and photons, moving with unwavering constancy, map these distortions. Their masslessness allows them to respond with perfect fidelity, tracing out the universe's geometry without resistance or inertia. In this way, photons become the universe's rulers, its measuring sticks, its clock hands, its narrators. To say they carry energy without mass is to say they are freed from the constraints that define massive particles. They do not rest. They do not age. They do not resist acceleration. They simply follow the contours of space-time, carrying their frequency like a gently humming thread that never breaks. And yet, this weightless existence does not make them fragile. High-energy photons, such as gamma rays released by neutron star collisions, carry energies millions to billions of times greater than visible light. When LIGO detected gravitational waves from a neutron star merger in 2017, telescopes across the world saw accompanying bursts of photons, gamma rays, X-rays, ultraviolet, infrared, radio waves, each part of the electromagnetic spectrum telling a piece of the story. These photons revealed the synthesis of heavy elements like gold and platinum, forged in the enormous pressures of the merger. Energy from the heart of a cosmic catastrophe, carried outward by massless travelers who brought to Earth the story of creation in its most violent form. Yet, even in that violence, the photon's delivery is soft. When that gamma ray burst reached Earth, it had traveled for 130 million years. Its energy had survived shocks, fields, turbulence, and expansion. And when it finally arrived, it touched detectors with the gentlest tap of frequency. Its masslessness allowed it to escape unscathed from events that would tear apart matter. In this way, the photon is both delicate and invincible, untouched by time yet capable of carrying the memory of cosmic upheaval across eras. This duality also appears in the way photons influence matter without penetrating it. When sunlight hits a solar sail in space, the pressure of its photons can push a spacecraft forward, millimeter by millimeter. The Icaros mission by JAXA demonstrated this beautifully. No engines, no fuel, only sunlight pushing against reflective material. Each photon transfers momentum, and though the push is small, the effect accumulates over time. Here again, energy becomes motion without mass, guiding technology across interplanetary distance in the quietest possible way. And so, as the quiet around you deepens, the presence of the photon becomes more than an idea. It becomes a sensation, a feeling of living inside a world held together by weightless messengers. Their energy is everywhere, woven into every sight, every warmth, every delicate boundary where matter meets light. They shape everything you know without ever inhabiting the world the way you do. Their existence is motion. Their essence is rhythm. Their gift is the ability to carry energy without ever needing mass. And as your awareness sinks even further into this soft current, you may begin to sense that photons form a kind of luminous nervous system for the universe. They move through galaxies the way signals move through neurons, carrying information, energy, and structure across distances that defy comprehension. In that vast scale, they connect the cosmic web, those immense filaments of galaxies and dark matter visible in deep surveys like the Sloan Digital Sky Survey. These surveys map the positions of millions of galaxies using the photons they emit, revealing a structure that resembles a neural network stretched across billions of light years. The photon, once again, becomes the messenger that unveils the architecture of existence. Its masslessness allows it to cross the void without losing direction, without softening beyond recognition, carrying the whisper of each galaxy's position into the instruments of astronomers. And within each of those galaxies, photons guide the evolution of stars. In dense molecular clouds where stars are born, photons struggle to escape, trapped in veils of dust and gas. As they attempt to move outward, their energy warms the cloud, influencing the collapse of matter into new suns. Infrared telescopes like Spitzer and JWST peer into these clouds using photons whose wavelengths are long enough to slip through the dust. These photons reveal star-forming regions hidden from visible light, painting soft, glowing images of young stars surrounded by swirling disks of gas. The energy they carry tells astronomers the temperature, density, and chemistry of regions that would otherwise remain unseen. Again, the absence of mass becomes a gateway to sight, allowing photons to escape where matter cannot. And while photons illuminate the vastness beyond Earth, they also shape the intimate rhythms within it. Plants use photons not only for photosynthesis but for signaling. Blue and red light influence growth patterns, triggering processes like phototropism, the tendency of plants to lean toward light. This was studied in depth by botanists and biophysicists like Winslow Briggs, who discovered how photoreceptor proteins respond to different wavelengths. The message delivered by a photon enters the protein, shifts its structure, and sets off molecular cascades that shape a plant's behavior. All of this begins with a massless particle carrying a fragment of star-driven energy into living tissue. Photons even influence geological processes. When cosmic ray photons strike Earth's atmosphere, they generate secondary particles that contribute to the creation of isotopes like carbon-14. This isotope forms when energetic photons enable nuclear transformations in nitrogen atoms, and it becomes embedded in organic matter. Archaeologists use carbon dating, based on the decay of carbon-14, to determine the age of ancient artifacts. In this way, the photon acts as a quiet timekeeper, embedding temporal signatures in the tissues of plants and animals, in wood and bone, in the entire archaeological record of humanity. Weightless particles shaping the calendar of deep time. And, as your breath slows into a peaceful cadence, consider how photons shape the edges of perception in animals far more sensitive than humans. Bees, for instance, see ultraviolet patterns on flowers, patterns invisible to you, that guide them to nectar. Birds perceive ultraviolet cues in plumage that play roles in mating and recognition. Deep-sea creatures emit and sense bioluminescent photons, surviving in places where sunlight never reaches. These animals navigate by signals that travel effortlessly across water, cutting through darkness, encoding energy without mass. In every example, the photon acts as a gentle translator between environment and awareness, shaping behaviors as varied as migration, hunting, communication, and growth. And deeper still, at the quantum level, photons define the very rules by which electrons inhabit atoms. Electrons occupy orbitals only because absorbing or emitting photons adjusts their energy levels. The quantization of light, discovered through century-spanning research from Planck to Einstein to modern photonics, determines the quantization of matter. Without photons, electrons would not settle into stable configurations. Atoms themselves would dissolve. Matter would lose its coherence. Photons without mass uphold the structure of every table, every mountain, every molecule of air. They define the architecture of matter without ever joining it. Feel the quiet gravity of that truth. The massless shapes the massive. And this becomes even more profound when you consider that the majority of electromagnetic processes involve photons that are never directly observed. Virtual photons, arising from the quantum fluctuations in the vacuum, mediate forces between charged particles. They flicker into existence for unimaginably brief moments, allowed by uncertainty, transferring momentum and energy before disappearing again. When you bring two magnets close to each other, the force you feel is carried by virtual photons. When electrons repel each other, the exchange of virtual photons enforces that repulsion. When atoms bond, electrons shift their clouds through interactions guided by photons you never see. In every case, The vacuum around you hums with these unseen exchanges, shaping the firmness of matter and the stability of the world. This idea was made mathematically precise by quantum electrodynamics, developed by physicists like Richard Feynman, Julian Schwinger, and Shinichiro Tominaga. In QED, the photon is not just a particle but the fundamental mediator of electromagnetic interaction. Its massless nature is essential, for if it had even the slightest mass, the electromagnetic force would weaken with distance. Atoms would become unstable, and the universe as you know it would evaporate into a different kind of existence entirely. The universe has chosen this precise configuration, a configuration where energy can move freely, unburdened by mass, encoded in trembling fields that never tire. And in the deep dark between galaxies, where matter is sparse and gravity stretches thin, photons still move with perfect clarity. Their frequency holds their energy. Their phase carries their history. Gamma-ray bursts, the most energetic events known, send photons so powerful they can briefly outshine entire galaxies. These photons travel for billions of years without losing their identity, without scattering, without obscuring the information they bring. They are witnesses to cosmic events that occurred when Earth was still molten. And when they finally arrive, they pass softly into detectors on mountaintops or satellites orbiting Earth, carrying no more mass than the faintest shimmer of moonlight on water. Even the boundaries of space-time speak through photons. When astronomers measure redshift, the stretching of photon wavelengths due to cosmic expansion, they uncover the rate at which the universe grows. This is how scientists like Edwin Hubble, and later the teams studying supernova, discovered that the universe is expanding, and that dark energy is accelerating that expansion. Massless light revealed the swelling of space-time. Massless light revealed the energy of nothingness itself. Massless light revealed a cosmos larger and more dynamic than anyone had imagined. And in this quiet room, far removed from the distant galaxies and supernova remnants, the photons that reach your eyes and your skin are part of that same universal tapestry. They are born of trembling atoms, of shifting electrons, of warm surfaces releasing their stored energy. They touch you gently, delivering their frequency, reshaping the electrons within your own cells, influencing your perception and guiding your awareness without you ever realizing it consciously. The light from a candle flame, flickering softly in a dark room, is a river of photons carrying the energy of chemical reactions. The glow from a screen is a flow of photons tuned by semiconductors and quantum wells. The faint scatter of moonlight is sunlight reborn through reflection. Each photon carries energy without mass because its existence is defined not by substance, but by movement. It is a pulse in the electromagnetic field, a pure whisper of energy with no weight at all. And as your thoughts grow looser, as the quiet stretches wide around you, you begin to feel how the photon invites you to consider a gentler kind of existence, one in which motion, not mass, becomes the essence of being. A way of moving through the world lightly, without resistance, without heaviness. A way of existing as a ripple in something larger, something steady and ancient. The photon reminds you that there are ways of being that do not rely on solidity or force. Ways of carrying meaning that are woven into frequency and presence rather than substance. Sometimes the simplest truth reveals itself in the quiet space between thoughts. Photons feel less like objects and more like phenomena unfolding through the fabric of existence. A photon is not an entity you could hold in your hand. It's a transition, a change, a subtle release of energy moving outward in perfect stillness. When electrons shift between quantized states, the photon emerges as the universe's way of balancing the books, releasing the difference in frequency rather than substance. Its weightlessness becomes part of its identity, not an absence but a refinement. Consider how light slips through the atmosphere, not as a single beam, but as countless vibrating threads that brush against molecules of nitrogen and oxygen. Rayleigh scattering, first explained by Lord Rayleigh in the 19th century, reveals why the sky glows blue during the day. Shorter wavelengths scatter more easily, while the longer reds and oranges travel straighter paths. What feels like the atmosphere revealing its color is in reality billions of small shifts in photon direction, each one carrying the imprint of its wavelength. Those weightless shifts create the canvas of daylight you've known since childhood. In deeper places, laboratories built for precision, photons reveal even subtler truths. Laser cooling experiments led by Stephen Chu, Claude Cohen-Tanuji, and William D. Phillips showed that carefully tuned photons can slow atoms to near absolute zero by transferring tiny increments of momentum. Each atom absorbs a photon, slows slightly, then emits another photon in a random direction. The net effect is cooling. Momentum transferred without mass, temperature lowered by the touch of something that carries only energy and frequency. These experiments confirmed beautifully that the photon's influence has nothing to do with weight and everything to do with rhythm. Other moments in science display the same quiet elegance. Picture astrophysicists studying the shimmering halos around galaxy clusters. Photons passing near these massive structures curve along the gravitational landscape, creating arcs and rings observed through gravitational lensing. Though weightless, they follow the shape of space-time exactly, revealing invisible structures of dark matter. The light cannot resist bending because mass doesn't guide its path. Geometry does. Through these curved trajectories, photons map the unseen architecture holding galaxies together. A different kind of scene unfolds inside your own body. Each time light enters your eye, photoreceptor molecules shift shape in response. Retinal flips from one configuration to another the instant a photon delivers its energy. This tiny molecular dance becomes an electrical signal, then a cascade of neural activity, then a visual impression. Your entire experience of sight rests on the ability of massless particles to convey energy with absolute precision. The photon touches nothing directly, yet it changes everything it meets. Even the quiet spaces between atoms respond to photons in delicate ways. Vacuum polarization, predicted by quantum electrodynamics, suggests that empty space behaves like a medium full of transient particles. A passing photon influences this cloud, altering the effective electric field of charged particles. Experiments at SLAC provided hints of these subtle shifts, confirming the vacuum's shimmering complexity. The photon, though free of mass, becomes a probe into the quantum grain of emptiness itself. Across interstellar distances, photons also guide the chemistry that forms planets and stars. Ultraviolet radiation in nebulae breaks apart complex molecules, shaping the chemical pathways that create water, organic compounds, and even prebiotic structures. Observations from the ALMA array and JWST reveal regions where photons sculpt filaments of gas into forms that will one day ignite as stars. Energy flows outward, massless yet mighty, turning cold molecular clouds into stellar nurseries. Closer to home, A photon reaching your skin does something equally remarkable. Its frequency determines whether it warms you, burns you, or simply passes unnoticed. Infrared photons deposit their energy gently, creating warmth. Ultraviolet photons deliver enough energy to break bonds in your DNA, a process scientists like Rosalind Franklin explored in Understanding Molecular Structure. Yet all these interactions begin the same way. A small packet of frequency encounters matter, and the shape of that matter determines what happens next. At cosmic scales, whole epochs are revealed by photons that left their sources long before Earth formed. The fluctuating pattern of the cosmic microwave background shows temperature variations of only tens of microkelvin. Yet those tiny shifts encode the seeds of galaxies. The photons from that era have been stretched by expansion until their wavelengths are thousands of times longer than visible light. Still, their energy remains consistent with the rhythm set at their birth. Their masslessness allowed them to survive the universe's evolution without distortion of their internal structure. Deepening into this calm, imagine how photons carry not just energy but structure. Their polarization states, orientation of their oscillation, encode information about magnetic fields in space. Missions like WMAP and Planck analyzed this polarization to infer conditions in the early universe. Photons, weightless and tireless, become archivists of cosmic memory. Their paths and orientations store details of long-faded events, releasing that information billions of years later into detectors humming quietly in mountain observatories and orbital satellites. Everywhere you look, photons translate the world. They trace the outlines of leaves in the afternoon sun. They draw the faint glow of city lights on a humid night. They reveal the swirling dust in a beam of morning light. All of these scenes are conversations between electrons and energy, between fields and frequency. Sometimes the photon's influence takes more unusual forms. In certain materials cooled to near absolute zero, photons can couple with electronic excitations to form hybrid quasi-particles called polaritons. These quasi-particles behave with properties neither purely light nor purely matter. Experiments in condensed matter physics explore how polaritons flow like fluids of light, creating condensates that mimic quantum phenomena on macroscopic scales. Massless energy merges with matter to create entirely new forms of behavior. Each hybrid excitation becomes a testament to the photon's ability to shape the world without ever being part of its mass. Elsewhere, the photon participates in nuclear interactions. During electron-positron annihilation, two photons are emitted back-to-back, each carrying half of the annihilation energy. The process reveals ERDMC2 in its purest form. Mass turned into radiation, substance replaced with frequency. PT scanners in hospitals rely on this principle, detecting those back-to-back photons to construct images of metabolic activity inside the human body. Your internal processes become visible by way of photons born from the conversion of matter itself. More quietly still, the temperature of the universe, currently about 2.725 Kelvin, depends entirely on the energy of photons in the cosmic microwave background. The cooling of the cosmos over billions of years is, at its heart, a story of photons stretching into longer wavelengths as space expands. The photon becomes a thermometer for all of existence, its energy marking the passage of cosmic time. Slip further into this gentle reflection. See how the photon does not resist the universe's changes. It adapts its wavelength, shifts its energy, embraces the curvature of space-time, moves with whatever geometry it encounters. Flexibility becomes its nature. Weightlessness becomes its freedom. Your breath rises and falls softly as the thought settles. To carry energy without mass is to be pure relationship. A photon does not possess energy like an object stores fuel. It expresses energy through frequency. It embodies energy through vibration. This is why it never slows, why it never ages, why it always moves at the speed set by the structure of space-time. It has no mass to ground it, no interior to hold it back. Its entire presence is motion. Emerging again into this subtle space, you might notice how photons shape not only what you see, but the very boundaries of what you can know. Even the deepest observatories, the ones built to catch particles far rarer than light, cannot escape the influence of photons. In neutrino detectors like IceCube, buried deep within Antarctic ice, photons are created when rare neutrino interactions generate faint flashes known as Cherenkov radiation. The paths of these photons form sketches of invisible particles, allowing scientists to reconstruct events happening in a medium so dark and isolated that only weightless light can speak from within it. A neutrino's presence becomes visible only because photons rise from the ice like whispers, carrying the silent imprint of the interaction outward. Far above the ice, at the edge of Earth's atmosphere, photons reveal even more. Cosmic rays striking the air create ultraviolet fluorescence in nitrogen molecules, a faint glow used by observatories like the Pierre Auger Observatory to study the most energetic particles in the universe. Even in these violent collisions, the photon does not bring mass. It brings clarity. The energy it carries becomes a signature the atmosphere briefly writes into light, allowing eyes and instruments to read events unfolding at energies beyond anything machines on Earth can create. A different perspective emerges when you consider the strange, elegant experiments that explore the quantum nature of information. In optical quantum computing, researchers use single photons to represent qubits that can exist in superpositions of states. Devices like integrated photonic chips, etched with waveguides narrower than a human hair, guide photons along branching paths where interference patterns encode computations. These photons carry information without mass, allowing logic to unfold through delicate differences in phase. They do not heat the circuits, do not introduce inertia, and do not degrade easily. Their indifference to mass becomes an asset, letting them slip through complex optical networks with remarkable stability. This same stability becomes a lifeline in quantum communication. Scientists have used photons to distribute entanglement between distant laboratories, between ground stations and satellites, even across hundreds of kilometers of fiber optic cable. Entanglement survives because photons glide through space with nothing to weigh them down. Their correlations remain intact, untouched by time, allowing secrets to be shared with absolute security. In this realm, the photon becomes a bridge between minds and distances, carrying patterns that remain hidden until the very moment of measurement. Other variations of the photon's nature appear in condensed matter physics. In certain engineered materials, photonic crystals, scientists arrange structures at the scale of optical wavelengths. These structures control how photons move, creating forbidden bands where light cannot propagate and channels where it flows effortlessly. The result is a kind of architecture made of transparency and reflection. By shaping these environments, researchers create waveguides, filters, even optical analogs of electrons in a crystal lattice. Here, photons behave like particles in a solid, but without the inertia or scattering that matter experiences. Their masslessness becomes a canvas on which new kinds of materials are drawn. Moments arise when the photon's presence feels almost tender. Light emitted by bioluminescent organisms, fireflies, deep-sea creatures, certain fungi, reveals communication shaped by evolution for beauty and survival alike. These photons carry signals through forest air, ocean depths, and humid twilight. They navigate darkness not with weight but with glow, carrying energy from chemical reactions into the open night. In some species, elaborate flashing patterns become a language, allowing coordination, courtship, and recognition. Even here, the story is the same. Massless particles shaping the contours of life through delicate exchanges of energy. Shift your attention to the emptiness between cosmic structures. Space is never truly dark. It teems with low-frequency photons left over from the formation of the first stars, from countless supernovae, from galaxies almost too faint to detect. This diffuse glow, the extragalactic background light, fills intergalactic space with a soft, nearly undetectable hum of radiation. High-energy photons traveling through this background interact with it, losing energy through pair production, revealing the density of faint, ancient light. The masslessness of photons enables this long-distance conversation between epochs, where one particle from a distant explosion speaks to another particle born from forgotten stars. Closer still, in the realm of fundamental physics, the photon appears in equations not as a substance, but as a necessity. Gauge symmetry, the principle underlying the standard model of particle physics, requires the existence of the photon. When Hermann Weyl explored the symmetries of the electromagnetic field, he found that the maths demanded a mediator with no mass. The photon arises naturally from this symmetry, as if the universe itself insists on having a massless carrier of energy to keep its laws consistent and stable. Physics did not invent the photon. The photon is the inevitable expression of a deeper harmony within the laws that govern fields. A different layer of truth emerges when you consider that photons define the boundary between what can be seen and what remains hidden. Objects much smaller than a photon's wavelength cannot be resolved by conventional light. For this reason, optical microscopes cannot see structures smaller than about 200 nanometers. Photons set the limit. They draw the line between the visible world and the quantum world. Only by using shorter wavelengths, X-rays, electron beams, or scanning probes can scientists see smaller scales. This boundary isn't arbitrary. It is the nature of vibration itself. A wave cannot resolve details finer than its own rhythm. Weightless though they are, photons determine the fineness of vision. Slip again into the thought of how these vibrations shape your inner sense of time. The ticking of atomic clocks is determined by photons tuned to exact frequencies. In cesium clocks, for example, the oscillation that defines 1 second is tied to the microwave photons absorbed by cesium atoms. Optical lattice clocks refine this even further using optical photons interacting with atoms like strontium or ytterbium. These clocks are so precise that if two were placed a single centimeter apart at different heights, their tick rates would diverge slightly due to gravitational time dilation. Photons make this delicacy possible, carrying frequency so faithfully that even the curvature of space-time alters their rhythm. Time itself becomes an echo of light. Reflect for a moment on how patiently photons accumulate their stories as they travel. Imagine a photon born in the chaotic swirl surrounding a black hole's accretion disk. It fights its way outward, losing energy as it climbs the gravitational well, stretching into longer wavelengths. When it escapes, it carries with it the imprint of the black hole's mass, spin, and temperature. Astronomers decode these imprints to understand the physics of extreme gravity. The photon becomes a messenger that survived the brink of the ultimate gravitational abyss, delivering its story across cosmic oceans with its massless grace intact. The same principle holds in the laboratory. When scientists cool atoms to near absolute zero and study Bose-Einstein condensates, they use photons to probe the collective quantum state of the atoms. These measurements must be gentle, because photons disturb delicate states with even the slightest touch. Yet their weightless nature allows researchers to use extremely low-intensity light to glean information without destroying the system. The balance between knowing and not disturbing becomes a dance in which photons are the only viable partners. Another domain where photons reveal themselves is in the study of planetary atmospheres. When spacecraft like Cassini, Galileo, and the Mars rovers analyze the composition of alien skies and soils, they rely on spectroscopy. Photons absorbed or emitted by molecules in another world allow scientists to decode its chemistry. The detection of methane on Mars, the study of Venus's thick clouds, the analysis of Titan's hydrocarbon seas, all came through photons interacting with matter across unimaginable distances. A rover sends a beam of light into a rock. The rock emits photons back. Those returning wavelengths whisper its composition. Even more subtle are the photons used in gravitational wave astronomy. Laser interferometers stretch their arms over kilometers of vacuum, measuring distances so precisely that even the gentle passing of a gravitational wave can change the pattern of light. The photons in these interferometers do not resist this stretching because they have no mass. They simply adjust their phase, creating interference patterns that describe how space-time itself has shifted. Through this fragile dance of phase and distance, humanity has heard the collisions of black holes and neutron stars. Within all these stories lies the same quiet truth. Photons carry energy not because they contain something, but because they are something. A frequency, a vibration, a trembling of the electromagnetic field so fundamental that it transcends the concept of mass. To hold energy without mass is to be pure motion, pure rhythm, pure exchange. The mind settles more deeply when you realize that photons do not merely illuminate the world, they choreograph its unfolding. At the quantum scale, photons nudge electrons into new configurations, dictating how atoms bond, how molecules twist, how proteins fold. This is not metaphor. It is the gentle arithmetic of quantum electrodynamics at work, the same arithmetic that governs every chemical reaction around you. Through photons, energy flows across thresholds, enabling transitions that matter cannot complete on its own. A photon arrives, an electron shifts, and suddenly a molecule transforms. A reaction ignites, a structure stabilizes. Energy delivered in weightless form becomes the architecture of life. Some phenomena reveal this architecture with remarkable clarity. In fluorescence microscopy, for example, biologists tag proteins with molecules that emit photons when excited. Under precise illumination, these molecules light up like tiny lanterns, revealing the choreography of life at the scale of tens of nanometers. Super-resolution techniques such as STED and PALM harness the quantum behavior of photons to push past the classical resolution limit, building images from patterns of emission, timing, and probability. Light, once thought too gentle to surpass its own wavelength, becomes a scalpel for seeing the unseen. Weightless photons carve clarity into the living world. Another quiet scene arises in the study of solar neutrinos. Detectors deep underground capture faint flashes produced when neutrinos interact with matter. These flashes are photons created inside tanks of heavy water or scintillators. Even though the neutrino is the central mystery, photons are the ones that speak for it. Their energy carries the story outward. A single interaction, a fleeting touch, a whisper of the solar fusion reactions that power every warm patch of sunlight on your skin. Neutrinos may pass through entire planets without stopping, but the photons they inspire let scientists understand the processes hidden in stellar cores. A very different insight surfaces when considering blackbody radiation, the spectrum emitted by any object with a temperature above absolute zero. Max Planck's work on blackbody radiation, which gave rise to quantum theory, showed that photons emerge in discrete quanta determined by temperature. These photons form the warmth you feel from a stove, the glow of heated metal, the infrared signature of your own body. Temperature is not merely a statistical property of matter. It is a dialogue between atoms and the photons they emit. The hotter the object, the higher the typical photon frequency. Here again, energy is carried without mass, and the language of heat becomes the language of light. Into deeper cosmic realms, another picture unfolds. The intergalactic medium, thin gas stretching between galaxies, absorbs and re-emits photons in ways that trace the history of cosmic structure. Neutral hydrogen in this medium emits photons at a wavelength of 21 centimeters when its electron flips its spin. Radio telescopes detect these photons to map the distribution of matter across billions of light years. The light is faint, slow, quiet, but relentless. Without mass, it crosses the abyss between clusters, revealing the scaffolding of the cosmos like a delicate ink drawing stretched across time. Further inward, into the structure of atoms, photons act as sculptors. The Lamb shift, measured by Willis Lamb in 1947, revealed that photons continually interacting with electrons shift their energy levels slightly. This unexpected discovery confirmed that the vacuum is not empty. The electromagnetic field, even at rest, flickers with virtual photons. Electrons sense these fluctuations, and their orbits adjust because of them. A weightless presence reshapes the geometry of one of the most fundamental objects in nature, the hydrogen atom. Physics itself had to change to make room for the photon's influence. Some of the most elegant experiments ever designed explore the photon's strange relationship with time. In delayed choice experiments inspired by John Wheeler, photons behave as though their past trajectories depend on measurements made in the present. A photon can travel through an interferometer in such a way that it seems to choose whether it behaved as a particle or a wave, only after the experimenter decides how to observe it. This phenomenon does not violate causality. It reveals the deep relational structure of quantum processes. The photon, weightless and timeless, does not store a fixed history. Its behavior crystallizes only when it interacts, as though its journey remains an open question until the final moment of awareness. Such ideas become even more profound when considered alongside quantum eraser experiments. When information about a photon's path is erased, even after the photon has been detected, the interference pattern can reappear. This suggests that energy without mass does not carry a classical narrative. It carries potential, coherence, correlation. Its story is not linear, but woven from all possible paths until the instant those paths converge into a single event. In this way, the photon becomes not just a carrier of energy, but a carrier of possibility. Stepping back from the quantum domain, sunlight yields another kind of revelation. As photons stream toward Earth, some collide with molecules in the atmosphere, imparting energy that drives winds, evaporation, and the movement of oceans. Climate scientists model these interactions with radiative transfer equations, describing how photons warm the surface, how clouds reflect them, how greenhouse gases absorb and re-emit them. Energy without mass controls the weather, shapes the seasons, and breathes life into every forest and ocean. The photon's influence is gentle but planetary in scale. Elsewhere, in the study of particle physics, photons reveal their power to transform. When electrons collide with positrons, their masses vanish into photons. Later, under the right conditions, photons can transform that energy back into matter. Experiments at SLAC and CERN probe these processes, demonstrating pair production, photon fusion, and other transformations governed by quantum field theory. Through all of these exchanges, the photon remains the purest form of transfer. No mass, only energy and information encoded in vibration. One of the more beautiful aspects of photon behavior appears in scattering experiments that reveal the roughness of surfaces. Shine a laser at a polished material, and the pattern of scattered photons produces a speckle pattern, a fingerprint unique to the object. Researchers use this property to study stress patterns in materials, vibrations in structures, even microscopic changes in biological tissues. The photon becomes a messenger, sensitive to every contour it meets, translating tiny structural details into a map of reflected energy. Further in, within the heart of living tissue, photons participate in a subtle rhythm known as photobiomodulation. Cells exposed to specific wavelengths of light, often in the red or near infrared, exhibit changes in metabolism, inflammation response, and energy production. Though the mechanisms remain under investigation, mitochondria appear to absorb these photons, altering their electron transport chains. This suggests a dialogue between light and cellular energy, a direct conversation between photon frequency and biochemical vitality. Another image arises when thinking about the earliest stars. These massive bodies produced torrents of ultraviolet photons that ionized the hydrogen in the intergalactic medium, ending the cosmic dark ages. This epoch of reionization, studied through observations of distant quasars and galaxies, marks a turning point when photons once again reshaped the universe. Light became the sculptor of cosmic clarity, dissolving haze and revealing structure. Even now, the remnants of these ancient photons wash across Earth, enriched by gravitational redshift, cosmic expansion, and interactions with intervening gas. They carry the story of the first stars, spoken across 13 billion years, arriving weightless yet laden with history. A final quiet thought settles into place as your mind drifts deeper. Photons do not struggle against the universe. They move in perfect harmony with it. They follow geodesics set by space-time. They transform their energy according to redshift or blue shift. They interact only when the world invites them to. Weightlessness becomes a form of surrender, a way of traveling through existence without resistance, without friction, without burden. Settling deeper into this unfolding stillness, you begin to sense that photons do not merely travel through the universe. they reveal the universe to itself. Every interaction, every shift, every faint whisper of light becomes a quiet unveiling of structure that would otherwise remain hidden in the dark. The cosmos speaks in frequencies, and photons carry its voice across distances so immense that time itself feels thin around them. Their masslessness is what allows this voice to remain clear, crossing horizons that matter could never reach. Some telescopes listen for this voice not by collecting images, but by decoding the redshift and blueshift of photons arriving from distant worlds. The Doppler effect, the stretching or compression of light due to motion, reveals the wobbling dance of exoplanets tugging on their stars. In the early discoveries made by Michel Mayor and Didier Queloz, the shifts in photon frequency exposed the presence of worlds no one had ever seen. Weightless light disclosed the orbits of entire planets, simply by changing its rhythm in response to motion. Elsewhere, in the heart of the Milky Way, photons from pulsars arrive in a perfectly timed sequence. Pulsars, rapidly spinning neutron stars, emit beams of electromagnetic radiation that sweep across Earth like lighthouse beams. Each photon in that rapid rhythm carries the signature of the star's rotation, allowing astrophysicists to measure time with precision surpassing the best human-made clocks. These stellar beacons pulse steadily for millions of years, guided only by the physics of gravity and the resilience of photons. Their timing reveals the mergers of neutron stars, the disturbances caused by passing objects, even the gentle waves of space-time that ripple through the galactic environment. Within your own life, photons create patterns just as steady, though far more intimate. Morning light, striking your eyelids, sets in motion biochemical processes that awaken the brain. Evening light shifts toward longer wavelengths, signaling the slow descent into drowsiness as melatonin begins to rise. The circadian rhythm that governs your sleep, mood, and alertness is woven from the arrival of photons across hours and seasons. A morning sunbeam contains no mass, yet it shapes the turning of your internal clock as faithfully as any cosmic pulse. Another image forms in the quiet, the photon as a traveler that never accumulates experience. It sees neither the length of its journey nor the passage of time between its birth and arrival. From its own perspective, the universe collapses into a single moment. Yet the information it carries remains rich, layered with the imprint of every field, every interaction, every gradient of space-time it has crossed. Even without time, it remembers. Even without mass, it influences. Even without rest, it continues. Somewhere in a laboratory, a physicist cools a tiny mechanical oscillator to its quantum ground state, using carefully tuned photons to extract energy from the system one quantum at a time. This process, sideband cooling, relies on photons to purify motion itself, reducing vibrations until the system rests at the lowest state allowed by quantum mechanics. Light becomes the sculptor of quiet, drawing away motion until nothing remains but the barest hum of the vacuum's own fluctuations. Massless energy calming massive matter, down to the final whisper. A softer scene emerges when you imagine a lone photon reflecting off the surface of a calm lake at dusk. The gentle ripple of its frequency holds the warmth of the day in one direction and the coolness of the water in another. When it reaches your eye, the experience is effortless, a shimmer, a color, a glint. Yet what your mind perceives is the end of an extraordinarily delicate journey, one guided by interactions shaped by the photon's frequency, its phase, and the moment it meets the molecules of your retina. Throughout all these stories, the photon remains unchanged in its essence. It never grows weary. It never slows down. It never settles into stillness. Its entire existence is an expression of motion, of energy carried through rhythm rather than mass. The universe uses photons to move warmth from stars to worlds, to map the geometry of space-time, to reveal the chemistry of distant clouds, to shape the behavior of living cells, to wake you in the morning, and to paint familiar colors across your memories. Even now, as the quiet deepens, this weightless traveler continues moving through the space around you. Every photon gliding past holds a tiny portion of the universe's unfolding. Each one arrives as a fragment of a story written long before it touched your senses. The more you settle into this thought, the more natural it feels. Something need not carry mass to carry meaning. Something need not possess weight to shape the world. The photon shows that energy itself can be presence, that rhythm can be reality, that motion can be existence. You breathe out slowly, allowing this truth to rest within you. In the photon's simplicity, the universe reveals something profound, a path of being that is effortless, continuous, and open to all distances. A form of existence defined not by substance, but by journey. A reminder that even the smallest tremor of light can cross a gulf of billions of years and still arrive with its message intact.